Hello guys, it's the Caribbean Bookworm, and in this video I wanted to be talking about some of the concepts of quantum physics explored in the Ant-Man movies in the Marvel Cinematic Universe, as well as in general some of the concepts in quantum physics that are often touched upon in those movies in general as well. I recently just came home to the Caribbean for a vacation, so I thought why not explore this topic in this lovely weather with some of my lovely friends, the cats, which is fitting for quantum mechanics, as well as the fact that the new Ant-Man movie just recently came out, which is even perfect to talk about this. So without further ado, let's get into this. First disclaimer for this video is going to be that one, I am just an undergraduate student. I am not a professional. If you want to see a more professional take on this exploration, I would heavily suggest you check out the video by Wired, in which an actual physicist talks about some of the concepts explored in at least the first and second Ant-Man movies. So heavily recommend you check that out. But if you still want to stick around and do some mental explorations in general, then stay tuned. I tried my best to use sources which are reliable, and I often try to allude to those sources so that you can check out these things for yourself. So without further ado, let's jump into the first concept, and that is shrinking down to the size of an atom, such as the little fellow right here really wants to do. So in the first Ant-Man movie, by the way, minor spoilers for, or at least spoilers for the first and second Ant-Man movie, and some spoilers for some of the Phase 4 MCU projects in general. No spoilers though for the third Ant-Man movies, as I myself haven't seen it yet, and also it's a very new movie, so I'm not gonna spoil that for you guys. In the first Ant-Man movie, Ant-Man basically accidentally shrinks down and gets to the size of the atom, and then goes even smaller than that, to the point at which you start seeing these very weird visuals that kind of try to encapsulate some of the weirdness of quantum mechanics. And this is often explored in other MCU projects as well. For example, in the first Doctor Strange movie, there is a brief moment at which you see Doctor Strange kind of hanging around in there in the quantum realm, as well as, of course, the second Ant-Man movie, and I would imagine, of course, the third new Ant-Man movie as well. Shrinking down to the size of an atom has its practical limitations, you could say, as shrinking down someone like Ant-Man means that you would have to shrink the atoms of which Ant-Man and his suit is made out of down to a smaller size than atoms themselves, which is a bit paradoxical, because that would mean you would have to make the space in between the atoms in his body and in the suit's body even smaller as well. And by today's means, we don't have an exact way to knowing how to do this without, well, the particles themselves being unstable and kind of, you can say, eradicating themselves. So by that means, it is unfortunately not possible to shrink down to the size of an atom. But for more in-depth exploration as to some of the limitations and what would happen if you were to do this, I would heavily suggest you check out the video by Koers Gezacht on the quantum foam, if I'm not mistaken, at which they explore what if someone could indeed shrink down to very small sizes, and at the end even down to the size at which Ant-Man tried to explore in the first movie. So that's a bit less exciting, but let's jump into some of the other things which are somewhat very exciting. And starting with that is the concept of superposition, which is very often explored in the second Ant-Man movie, and that is with the character of Ghost. The main antagonist in Ant-Man and the Wasp is this villain known as Ghost, which wears a really cool grayish white suit and is able to move around and kind of be like this blurry thing as she's fighting or as she's moving around. And this blurry thing is explained to be her being in superposition. And this is a very real thing in quantum mechanics. Before I go into this, note that in all of the points of which I'm going to be talking about, I'm going to be referring to what is known as the Copenhagen interpretation of quantum mechanics. As quantum mechanics is a very modern theory which is very useful and very be applied in a lot of sense. Most of our technologies run on quantum mechanical principles, but the actual physical meaning and interpretations behind some of the concepts used in quantum mechanics is still actually up to debate of natural philosophers. But one of the main interpretations of quantum mechanics is the Copenhagen interpretation, and that is the concept used in quantum mechanics, which is basically the wave function, which describes something like a particle, like an electron. The wave function is interpreted to be a sort of a probability smear of where the electron could be in space, or what its momentum, energy, or some of its other physical quantities could be. It is a way at which you can capture all of the discrete possibilities you can have with the quantumness of the thing. And once you do a little bit of trickery with the wave function, something known as the Born rule, then basically you do something that is called squaring the wave function or normalizing the wave function, and that basically gives you the measurements which one actually observes in an experiment. And long story short, in the Copenhagen interpretation of quantum mechanics, you think of a particle when you have its wave function as being in a superposition of all of the states it can be in. So for example, if you have an electron in a box which can be at just two positions, it can be at position A or position B, then the wave function would describe, well, a probability distribution of the electron being in one place or the other. It can say that, for example, there is a 70% chance of the electron being at location A and a 25% chance of it being at location B. And when squaring the wave function or doing the Born rule on the wave function, then you basically get some measurements and you know that the electron is exactly there or there. And until you normalize the wave function, then according to the Copenhagen interpretation, the quantum system is actually in both states. It's in a superposition, you could say. And the superposition concept is what they try to use in Ant-Man and the Wasp as well, as Ghost was basically at many places at the same time due to this fuzziness effect of quantum physics. Another cool name and concept which they've used in the Ant-Man and the Wasp movie is the concept of quantum tunneling. I say another cool name because in the Ant-Man and the Wasp movie, it was just a lab and they called the thing which they needed to do to get to the quantum realm a quantum tunnel, you can say. But in reality, physicists don't talk about quantum tunneling as if to actually tunnel through the quantum realm or something. It is a phenomenon which occurs due to the effects and consequences of quantum mechanics. This same wave function we talked about earlier, used to describe a quantum system like an electron or whatever it is you want to model with quantum mechanics, actually has another interesting effect. And that is that in a classical system, if you have, for example, I'm going to use the analogy of a ball. If you have a ball that is in a well, you can say, then in order to overcome, well, the well, and in order for the ball to actually get out of the well, you need to provide the ball with enough energy so that it can actually roll upward and get over the edge of that well and actually leave the well, right? That makes very intuitive and logical sense classically in our mind. If instead of a ball, we had a water pond, you can say, in this well, then the same principle and rule would apply. You need to provide enough energy so that the water could spill out of that well. Classically, again, this makes sense. But in quantum mechanics, however, there is this weird tricky bit at which the wave function that describes a quantum system could actually leak out of the boundary, you could say, of that well, regardless of how thick or how high the well is. And in jargon, in physics jargon, people that have taken a course in quantum mechanics have heard of this way too often, as referred to as the infinite square well problem. But without that jargon aside, this basically alludes to the fact that regardless of how high potential energy of a system is, like regardless how much energy you need to do something, you could say classically, in quantum mechanics, there is a very small but non-zero probability that that something is done because of the fact that the wave function actually leaks out of the boundary of whatever that potential barrier is. So that's a lot of jargon, but that basically means that, for example, if I were to throw a ball towards a window, you could say, then I would need a certain amount of energy put into that ball so that the window actually breaks, right? But in quantum mechanics, there is a small probability, but non-zero one, that regardless of how I throw that ball, it actually is able to go and break that window or tunnel through the other side of the window. So it is a very cool phenomenon, and it is one of the things which Ant-Man and the Wasp also talks about. And Ghost actually does this, but I do not remember if they call it quantum tunneling or just teleporting in the movie. The next concept that I wanted to talk about from the Ant-Man movies is the concept of the quantum foam, or the quantum realm, actually. And it is explored, of course, in the first Ant-Man movie. It is alluded to. In the second Ant-Man movie, they talk about it a little bit more, and I imagine that in Ant-Man and the Wasp: Quantumania, they explore this even further. And even in Avengers Endgame, it is actually alluded to, but we're going to talk about that later on, the one in Avengers Endgame. But the quantum foam is this idea that once you go down to the very, very small scale, you get to a point at which basically, if you have your typical description of space itself, or even if you want to get more fancy with it, and a more technically accurate space-time, as basically a theory known as general relativity, proposed by Albert Einstein, unifies space and time itself, as it is one cohesive thing known as space-time on which everything happens. Well, the idea of the quantum foam is that if you go down to a small enough scale, the space-time is not actually uniformly flat anymore. And the reason for this is not because there's mass and mass curves spacetime, which you might have heard if you heard talks about black holes and things like that. No, no, no. The reason why spacetime is not flat down to this scale is due to quantum mechanics itself. That is the proposition, at least. Due to the fact that in quantum mechanics, there is this thing known as the Heisenberg uncertainty principle that states that due to nature itself, there is a limitation at which you can know the position and the momentum of something. So you cannot exactly know the position of something like in space at a certain scale. And when you get down to these really, really small scales, you tend to bump into those limitations. So the space-time or the quantum foam, you could say, would appear as this jittery mess instead of a still space-time, you could say, stage. And it would appear as if you're boiling water, and when you're boiling water, or maybe there's a better analogy, which I will put a GIF of right here. You can see this jittering effect due to the uncertainty principle happening. And in this jittery mess, you have the place at which some of the more deeper concepts of quantum mechanics actually lie. Actually, there's a more profound theory than just quantum mechanics out there, known as quantum field theory, which describes a lot of the particles and fundamental particles in nature as being, you can say, these small lumps or perturbations in official lingo of these various fields which permeate space-time itself. These bumps in these little fields, like the electron field or certain quark fields and things like that, are actually caused, or the way they interact with each other, these different fields, are due to something known as virtual particles, which are particles which can be created and destroyed almost instantaneously, which is a very bizarre concept and might appear like fantasy if you don't know much of quantum mechanics. But there is a little bit of evidence of particles popping in and out of existence from something known as the Casimir effect, which is a concept explored by the Dutch physicist Hendrik Casimir. In a paper in the 1940s, the late 1940s if I'm not mistaken, Hendrik Casimir explored a concept at which you have two non-conducting plates, if I'm not mistaken, placed really close to each other. And the argument was that if you have two non-conducting plates, they shouldn't experience any attractive force. But turns out that they did. And one of the propositions to explain this phenomenon was due to the actual virtual particles being created on the outer edges of these plates, you could say, in contrast to the ones on the inside, and the ones on the outside having a higher concentration than the ones on the inside. Of course, there are other, you can say, alternative explanations for the Casimir effect, like there being perhaps just van der Waals forces between the plates and such. But as of this moment, this is one of the most convincing evidences you can say of virtual particles, things being created and destroyed out of nothing, being an actual thing that nature actually does. So the quantum foam and the idea of the quantum foam actually touches upon some very fundamental physics. And I'm very happy that the MCU is trying to explore this with, for example, the quantum realm. And I would imagine, especially the third Ant-Man movie, the new one, to talk a lot about this, especially seeing some of the visuals in the trailers and such.
Give us a second chance.
Let me make this easy for you. You will bring me what I need, or everything you call a life will end.
For the last two concepts, things are going to get really deep. Things are going to get very speculative, and even I'm very uncertain, no pun intended, as to how things are going to go. So I try my best with this. Stick with me. If I'm wrong about something, correct me, but I will try to allude to where I've heard and like read about these things to be as more concise as I can with them. In this next point, I want to talk about the fact that in Avengers Endgame, Ant-Man was one of the key players. In my opinion, he saved the universe, like in a lot of sense. Even though Tony Stark made the sacrifice, Ant-Man, if Ant-Man didn't get out of the quantum realm, things would have ended very differently. Because him getting out of the quantum realm, it's inspired Tony Stark that, oh, maybe time travel is possible somehow through the quantum realm. And though, of course, in Marvel, this is very sci-fi, and a lot of it is actually just throwing words that make scientific sense in a very non-scientific way, there is an actual legitimate idea behind this concept of, well, not per se time travel, but something very closely related to time travel, related also to quantum phenomena. And this is a very deep and profound idea known as the EPR equals ER. It is a very hot topic right now, and it is cutting edge physics, very uncertain, but there was a lot of fuss about it actually very recently. And the whole idea is that this is separated into two bits, EPR and ER. And this is a theory of quantum gravity, which is one of the holy grails right now that physicists, theoretical physicists especially, are looking for. They're looking for a theory which can somehow unify our notion of gravity with our notions of quantum mechanics. And EPR is a paradox proposed by Einstein, Podolsky, and Rosen. And this paradox entails a concept in quantum mechanics known as quantum entanglement, which is also explored actually in the second Ant-Man movie a lot, but I thought very poorly. But this concept of quantum entanglement is that, well, in quantum mechanics, you have the notion that if you have two particles, somehow their wave function, as I've talked about a lot earlier, their wave functions are somehow interrelated to each other in a way that if you measure one particle, what its state is, you immediately know what the state of the other particle is. And a lot of times then the notion is that if you measure, say, an electron and it has a spin up, then you immediately know that the other electron has a spin down. But there are problems with this, especially with Einstein's theory of special relativity, as the idea of the EPR paradox is that this shouldn't be true in a universe that we live in, because, for example, we know, especially due to Einstein's special theory of relativity, that things cannot move faster than light, or you can say cause cannot happen faster than light, basically. Even though it's called the speed of light, more accurately, I should say the speed of causality that happens to be in our universe, the speed of light in a vacuum. And the way in which this EPR paradox exploits this notion of quantum mechanics is by stating that if, for example, you have two entangled particles and you move them away, like at the edges of the universe, then no matter how far you move these particles from each other, if you do a measurement of the other, you immediately still know what the state of the other one is. And if you go by the notion that observing something in quantum mechanics actually has an effect on the wave function and kind of collapses it and gives you the state, then that means that by measuring the one particle right here, it might have had to send information or a signal to that other particle in order for it to also collapse and have a particular state. And that sending of the information, well, if the moment you know this one, you immediately know the state of the other one, it implies basically that you know something instantaneously, which is very much against, well, the theory of special relativity, because especially if you separate them like by a whole universe, that means that the signal must have had to travel faster than light, as not even light is able to travel across the universe instantaneously. So this becomes a big problem, and there are ways at which physicists have tried to work on this and resolve this with things like the Bell's theorem and Bell's inequality. Even one of the recent Nobel Prizes were on Bell's inequality, and it has to do also with some of the interpretations of quantum mechanics itself. But keep in mind this notion of entanglement. On the other side, I mentioned EPR equals ER, and that is something known as ER is the Einstein-Rosen bridge. And if you've seen maybe the first Thor movie, or any of the other Thor movies, you might have heard that term a lot. And the Einstein-Rosen bridge is a fancy way of saying a wormhole. So basically, this notion connects the idea of entangled particles with wormholes, saying that basically when you have entangled particles, actually you have microscopic wormholes, which is a very ambiguous idea. And it was proposed, or two of its main pioneers is Leonard Susskind, which is very known for his very accessible lectures out there on physics. He's an American theoretical physicist. And you have the Argentinian physicist Juan Maldacena, which amongst professionals especially, is very well known as one of the main contributors to the field of string theory. He came up with something known as the holographic principle, which is a very technical thing which helps string theorists and people studying black holes to look at these very complex phenomena, though not having direct access to them. So Madasena and Susskind came up with this notion that wormholes are somehow related to entangled particles, and wormholes themselves have a thing or two to do with time travel, especially if you've read a lot of sci-fi, in the simple fact that if one enters a wormhole and exits it at another end, basically, if you have a traversable wormhole, and if the exit of this wormhole happens to be at a place that is in the past, or in your past, for example, it is a way at which you can not only travel through space but also time. So it is a way at which you can make time travel somehow make sense. It's still a bit problematic because you have the problem that basically you cannot time travel earlier than you were able to create wormhole, and also you have things like closed time-like curves that basically creates things like the grandfather paradox and things like that. So there's a lot of problems with time travel already, and it's one of the reasons why time traveling to the past, at least, is not something which has by far been shown to be possible. But if there's any way in which you can connect the quantum realm, I think, to this notion, this big notion of time travel, especially the way they did it in Endgame, I think this might be one of the ways especially which you can do it. There are links down below in the description if you wanted to read more about the EPR equals ER thing, both for the layman and for the hardcore people that want to read papers. So yeah. The last notion that I wanted to explore is the concept of the multiverse, which, if you know anything about the MCU, Phase 4, Phase 5, or maybe you've seen the third Ant-Man movie already, you know, or the Loki series in Phase 4, you know that the multiverse is becoming a big thing right now in Marvel. Like, it's the next big thing next to Thanos or something. And for a good reason. It brings up good story writing material, especially if you want to go bigger than a universal threat like Thanos. So the multiverse, so I'm not going to talk about how the multiverse plays out, especially with Kang and maybe some of the things explored in Loki and such, but I am going to talk about some of the legitimate ways in which physicists have gone about the multiverse idea, and especially how it might relate to Marvel. Well, the multiverse, earlier we talked about the concept of the Copenhagen interpretation of quantum mechanics, and now it's one of the many interpretations you can have about quantum mechanics. And now this is going to very much come into play, because the Copenhagen interpretation states that the wave function you have that describes a particle or a quantum system is this probabilistic thing of sorts, at which when you do a measurement, it collapses the wave function and you get to know what's actually there or not. But But there are other interpretations of quantum mechanics, two of which is, for example, the pilot wave interpretation, which is a very interesting, different interpretation that states that, oh, maybe this wave function is an actual thing, like you have all of these different like probability distribution of the energies, the momentum, or the positions of a particle, and actually the particle is able to traverse all of these positions or whatever states it can have, but due to some finicky hidden variable, then basically you have that effect basically that is like the squaring of the wave function, and then it getting just one of those different effects. But basically it is like the particles is riding this wave, you could say, until basically you measure it and it has a particular finite value. So it's a very interesting theory, but it's not the one that we're interested in for the multiverse purpose. For the multiverse purpose, we're interested in one called the Everett interpretation, or more famously known as the many worlds interpretation. There are many modern science popularizers, such as most notably people like Sean Carroll, which heavily believes that the many worlds interpretation is the one to go for quantum mechanics. And it states basically that when we do that squaring of the wave function and we get our observables, we know where the electron is, in a manner of speaking, that basically all of the other like probabilities that the system might have been able to take are not actually disregarded. They actually exist, but they branch out into their own separate universe. So you have this branching out of universes based on every single, you can say, time you try to do this observation effect, basically, in quantum mechanics. So by this notion, you have pretty much an almost infinite number of universes based on every single time an observation or an observable was made in the quantum mechanical sense. And this is a very, very insane way of looking about it, but it is a way which legitimate scientists are thinking about this. Of course, one of the many problems with this interpretation is that it's very hard to actually test it, as in science, in order to be able to verify something, you want to be able to test it. And something like the multiverse is difficult to test because it's almost, or as far as we know, impossible to interact with these branching universes. But it is an idea, and one of the cornerstones behind this idea that makes it so profound and interesting is that it lies behind this concept known as a universal wave function. So instead of describing just an electron or a small particle as a wave function, it actually attempts to describe the whole universe as a wave function, which is insane, but it is useful because it can tell you, if you describe the whole universe itself as a wave function, it can tell you things like the boundary conditions of the universe, how its initial states were, like what happened, for example, at the near the beginning of time and at the early universe. And as a matter of fact, there is a very interesting, very technical thing that is pretty much captures the imagination of a lot of theoretical physicists and even aspiring ones such as myself, and that is something known as the Wheeler-DeWitt equation, which is, I'm not going to talk too much what it entails, but basically you have the wave function, a universal wave function, a wave function describing the whole damn universe. And in order to try to unify like quantum mechanics and gravity, it imposes a constraint on this universe wave function by doing an operation onto it, by doing some sort of mathematical thing to it known as a Hamiltonian operator that has all of the gravity components in it. So this Hamiltonian operator is a thing of quantum mechanics, but basically it says something about the total energy of the system, in this case the total energy of the universe, and in this Hamiltonian you have the gravitational constraints of your universe, and this gravitational constraints being something to do with Einstein's theory of general relativity and how that describes gravity. So by doing that constraints to your wave function of the whole universe, you get a result that equals to zero, and this has very profound implications for theorists, and it helps you to look at ways in which you can describe the whole universe in terms of, well, just one single elegant equation. And of course, with the avert or with the many worlds interpretations, this can have not just implications for our universe, but if you believe in the many worlds interpretation, it can tell you things about all of the other universes out there as well. So it's some very profound stuff. And I think if you're curious about this, I heavily explore you to dabble more into this, but it does get very technical. So that's a bit of a warning. But yeah, so in general, those were the concepts which I wanted to explore with Ant-Man and just in general with the MCU.